Hello, what I'm going to try to do today is introduce the whole idea of earth science, or what I call geosciences. And basically what geosciences are, we talk about the earth in the middle, and again you can actually do the earth a different way. You can draw a circle with a cross in there showing the four elements: earth, wind, fire, and water. But what we're going to talk about is geology, which actually makes the hard surface of the earth and everything inside, where we'll talk about mafic and felsic, whether we talk about oceanic crust or continental crust. We'll talk about the mantle, we'll talk about the outer core, the inner core, we'll talk about convective forces inside, which drives the whole idea of plate tectonics, as well as actually making the continental rock more felsic, where we have feldspars and quartzes, and the oceanic rock where we have more mafic rock like basalts and or gabbro if it's intrusive or extrusive. So we'll talk about all that stuff, as well as wearing away the rock and putting down onto the ocean floor or in valleys and whatever. So this is geology. Then we'll move over to astronomy, and astronomy will start from the Big Bang, way far out, talk a little bit about distances and how we determine the distances, all the way into the solar system. This is actually a picture of Saturn. It's being illuminated by the sun, which is on the far side of Saturn. This is from a unmanned spacecraft. And if you take a look right here, there's a little itty-bitty dot looking back from Saturn toward the sun. That is the Earth. So the Earth actually made it into the picture. So we'll talk about hydrogen making up 99% of the universe, and we'll talk about stars. We'll talk about the balance of stars, stellar equilibrium, heat trying to make the star explode, gravity trying to make it implode, and when they actually meet that balance called stellar equilibrium, we actually have a star. We'll talk about lives of stars. We'll talk about all kinds of stuff in astronomy. Then we'll go down into oceanography. And oceanography will actually talk about everything that's actually in this picture. We'll talk about currents, both at the surface and density currents in the body of the ocean. We'll talk about the evaporation and then condensation, talking about the clouds that form. We'll actually move these clouds over, where most of it, because the ocean makes up more than 70% of the Earth's surface, most of the developing precipitation, whether it be liquid and or solid, falls back in the ocean, but it also allows water to make it onto dry land for all of us land creatures. We'll talk about evaporation, which is actually a cooling effect. We're actually heating up the water, so we're moving that heat back into the atmosphere, which cools the ocean. And we'll talk about the precipitation as being the opposite. We'll talk about it heating up, which actually causes that. We'll talk about the mixing of these bodies, and basically the ocean has a surface area which doesn't want anything to do with any of the areas that are below it. And again, density, the most common word in earth science, we actually have density differences in here. And the last thing, we'll talk about meteorology. And meteorology talks about our atmosphere, and talks about the interaction of the ocean with the air. We'll talk about cold fronts moving along the surface, what they can do to the atmosphere. We'll talk about warm fronts, what they can do and what they actually mean. And then we'll also talk about where they actually meet, where we're going to get stationary fronts and or occluded fronts. But basically where we get these bands of clouds, we have these fronts moving. We'll also talk about hurricanes. We'll talk about tornadoes that can spawn from these cloud masses. We'll talk about precipitation. We'll talk about wind. We'll talk about all kinds of things. But these are what are called the geosciences. Okay, anytime we talk about a science class, we have to talk about observations and measurements. And basically, whether we're talking about geology, oceanography, astronomy, meteorology, we're talking about physics, chemistry, biology, or any of the other sciences, what we have to do is we have to use our senses. And we have 5 senses. We have sight, we have hearing, we have taste, we have touch, and we have smell. Our sight actually is by rods and cones. Rods see the black and white, which we use for actually showing you probably the flight or fright, where we actually either run away from or we run toward things. We can use the cones for color. We have hearing, auditory nerves in your ear, with your eardrum starting all those little small bones and getting them going. We have olfactory nerves in your sinuses, in your nose, which actually can do smell, which does most of your tasting, believe it or not. We have taste buds in your tongue, which actually can do salt, can do spices, can do temperature, can do sweet. But if you actually want to tell the difference between sugar, as in chocolate, or sugar as in like mint candy, you need your nose to do that. And then we have nerves, which actually allow the touch, the free nerve ending, which kind of brings in the signals from all kinds of things to actually move them to your notochord up to your brain. And then you have this Messier, it's probably not Messier, Meissonier corpuscle, and this is actually a bundle of nerves which is in your skin and allows you to do the light touches, where you can feel like air moving over your skin, or you can feel the lightest touch of something on your skin. So those are your five senses, and we're going to use those to make observations. An observation is actually using your senses to measure something that you can actually see, hear, taste, touch, or smell, and record it. Normally we use tools for length, for volume, for mass. We use these tools, and then we actually use different measurements, whether we're using larger numbers, because yards can get so big that sooner or later we had to say, we have over 1,100 of these things, and all of a sudden we have to change it into 1 mile. Or feet, we have over 5,200 of those things, we call it a mile. If we get too many cups, we get gallons. We get too many gallons, we start talking about cubic yards. When we talk about mass, we actually have where we talk about grams, or we talk about kilograms, or megagrams. And if you take a look at these, the decimal point, these things are all less than 1 unit. Like this would be if this was meter. Decimeter is a tenth, centimeter is a hundredth. So we have 0.1, we have 0.01, we have 0.001 on, and then deca, this is where we have like 10, or hecta, which is 100, kilo, 1,000, and it keeps getting on. You guys all know now mega. When we talk about computers, we had kilobytes, then we had megabytes, then we have gigabytes, and we have terabytes, and sooner or later we'll actually know what's even bigger than that. Decimal point, same sort of thing down here, tens, hundreds, thousands, millions, where we talk about our system, which is the standard units, or we talk about the SI units, standards of international standards of measurement, which the entire universe uses. Everybody but America, of course. And then we have conversions where we take kilometers into miles, we can take yards into meters. You can see all those things. So we have observations. We use observations, we use tools to gain measurements, and this is all of what science is about. Next thing is inference and observation. Inference is actually using your senses to make predictions that may help you come up with conclusions in an experiment. You just got to be really careful with inference. I'm going to do an inference PowerPoint, so I'll show you that thing, and there are some examples of inference. Observation is a much better way of actually looking at things, and then using the units. The important thing is units, to actually look at these and to qualify them rather than just quantify. Then we're going to talk about scientific notation. Scientific notation is actually taking a large number and writing it into a smaller number, but keeping track of what it used to be. And what you're doing right here is you're taking that decimal point right there and you're moving it over 1, 2, 3 places, putting it at 5.780, significant figure, times 10 to the third. Or if we have negative 2,000, move it over 1, 2, 3, 4. We still keep that negative 2, but we take the exponent of 4 to actually show there were 4 And then if we can do numbers smaller than 0, this does not mean a negative number. This means a negative number. This is a positive number. And then we're moving it over 1, 2, except now we're moving it over to the right, so we say it's a negative motion. And you can see the same things here, same things there. You can also take an exponent like this and now move it over 1, 2, 3, putting a 0, and actually come up with the same number we started up here. Or you can do this one, negative 2, move it over 1, 2, adding a 0 there, come up with the same number we had on this way. So you can move them both ways. Okay, that's it for introduction. I probably will be doing something for scientific significant figures, although I'm not going to do that in this video. I will do that on the next one. But basically there are rules that you use for significant figures. I might as well go ahead and start doing this. This is a way of actually reporting values that are important in terms of quantifying or not so important. Any non-zero numbers like 1, 2, 3, 4, 5, 6, 7, 8, 9 are always significant. They're always important. All zeros between non-zero numbers, like if you had a 1, 0, 0, 0, 0, 2, 0, 0, 0, 3, all the zeros that are in there are going to be significant. All zeros which are simultaneously to the right of the decimal point at the end of the number are always significant, and I'll show you that when we get down here. And all zeros which are to the left of the written decimal, like this one right there, are always significant. Okay, so if we take a look at this number right here, these numbers are all non-zeros. We have 5 numbers, we have 5 significant figures. That's rule number 1. All non-zeros are always significant. This one, all non-zero, we have 4 of them. Again, rule 1. This one has a non-zero and a non-zero with zeros in between. This actually is significant with number 1 because we've got those significants. It's also number 2 because we have non-zeros and all zeros which are to the left of a written decimal point. There's the decimal point right there, and to the left these are always going to be significant. So we have 1, 2, 3, 4, 5 significant figures with rules 1, 2, and 4. This one actually only has one significant figure. Any number right there, and if you take a look, number 4, all zeros which are to the left of a written decimal point are always significant. These guys are to the right of, that's to the left. So we actually have one significant figure, which is the 4, but we have to keep track of the exponents. So we actually have 4 exponents. That's 1 and 3. This one, we actually have 8 and a 1, but anything that's on this side is always significant, so we have 5. And that's every non-zero, and that's also zeros which are simultaneously to the right of the decimal point. Okay, so those are to the right of the decimal point, so there's all significant. This one actually has all significant also, so we've got 6 significant, and that actually does all 4 of the rules. This one has 1 significant with 6 exponents, and this one has 3 because it's all to the right. So this is significant figures, and I'm going to have my kids do a worksheet on significant figures so they can actually figure out the importance of important numbers versus not so important numbers. And then the last thing, this is Apollo 8's Earth rising. This was the first time we actually got to see the Earth rise above another celestial object. This is from December 24th, the day before Christmas, 1968. William Anders on Apollo 8 snapped this picture. Took actually a couple in succession. I have one of these in my classroom. And I just wanted to show you, gave some image of how delicate this layer of atmosphere which protects us from everything is, and it is just the smallest, thinnest layer that's there. If you want to see a couple videos from the Earth from space, there's a 7-minute video right there, and this one is a high-definition 23-minute video of all of NASA put together for this. Okay, thank you very much for stopping by. Bye-bye.